Welcome to the COPRI Coastal Engineering Sciences Committee Technical Lunch and Learn. This is the second in a series of webinars that we've organized. And we plan to do these about every 2 months or so on varying topics that relate to the people with an interest in the coast. So whether they be engineers, scientists, planners, local officials, residents, whoever it may be, if you have an interest in the coast, we're trying to provide some technical presentations to allow for some knowledge transfer. So from what I've seen so far, we have about 110 people registered for this webinar, and that covers 28 states and over 20 countries. So our committee is pretty excited about that. So some of you are probably familiar with COPRI and others may not be. COPRI is the Coasts, Oceans, Ports and Rivers Institute of the American Society of Civil Engineers, or ASCE. And within COPRI, there are many opportunities for interested practitioners to get involved either through local chapters, technical committees, student chapters, and in other ways. So if you're interested, check out the COPRI website to find out some more information. So we've opened this up on an international platform and hope that it fosters discussion and idea sharing during these days with limited opportunities for in-person conferences and workshops. One of our committee initiatives is public outreach. So that's been pretty challenging over the last year or so. And we felt that setting up this webinar series was one way to meet that initiative. And while we call it a lunch and learn, we realize that there are attendees from all over the globe. So maybe this is a breakfast and learn, or a dinner and learn, or some other and learn. But no matter what time it is, we're glad you're here. So on to today's presentation. I'd like to introduce Dr. Ben Hamilton, who is a research scientist in the Sea Level and Ice Group at the NASA Jet Propulsion Laboratory. So Ben studies global and regional sea level changes with a particular focus on using satellite observations to understand sea level variability on interannual to decadal timescales. His work seeks to bridge the gap between scientists and decision makers and the challenge of generating useful scientific information for planning purposes. Ben is the current team lead of the NASA Sea Level Change Science Team and a member of several different research initiatives and teams, including the World Climate Research Program, or WCRP, Grand Challenge on Sea Level. So today, Ben will discuss aspects related to the NASA Sea Level Change Team, from observation to actionable information. We plan for Ben to speak for about 35 minutes, which will leave plenty of time for questions and discussions following the presentation. So please type your questions during or after the presentation using the chat feature, or use the raise hand function after the presentation. We had a great round of discussion after the first webinar, and we hope to do the same today, but we won't be taking any questions during the presentation just due to the difficulty of doing that over a virtual setting. So type them in the chat, or after the presentation, just use the raise hand and we'll work to get to every question that's out there. So with that, I will let Ben take it away. We'll have Ben controlling the slides here. We'll see if we can transfer over to Ben, and Ben sharing his screen.
All right, can everybody see that first of all?
I can see it, yes.
Okay. All right, thanks, Chris, for the introduction, and thanks for the invite to speak to you all today. Exactly as Chris said, I mean, the goal today is to talk to you a little bit about the NASA Sea Level Change Team, and really cover the full breadth of what we're trying to do with that Sea Level Change Team. And there's two particular things here. Yep, two particular things I'm going to address. One is, how does NASA actually measure sea level change? So what observations are we using? And then what is the NASA Sea Level Change Team, and what are we trying to accomplish? So I've got this first little cartoon here, and it's not at all to insult the expertise of anybody in this room, but it's really just a jumping off point for how I'm going to organize the observations that I'll discuss in the following slides. So this is just a really simple cartoon of sea level in the past. You have these different contributors that, for a very simplistic way, they stack up. And when you reach a certain level, they can cause flooding at the coast. So this is at some period in the past. Now there's additional drivers that have been occurring over the past century plus that cause sea level to increase. And this gap between your normal high tide and flooding conditions is really significantly narrowed. So some of the additional factors, we have sea level rise associated with ice and thermal expansion warming, which I'm going to talk about and how we observe those on the subsequent slides. we also have subsidence that's a factor as well at the coast. So these different things combine and affect the impacts that we see at the coast. So just in terms of organizing the rest of the slides that'll follow, you could break these down by spatial scale. So we have local drivers, we have regional drivers, and we have global drivers. And those are a couple of them that I'm going to cover today, are the regional, the global, and then also what's happening at the coast with subsidence. So NASA has observations. We have observing platforms where we can really go in and understand these processes and how they contribute to sea level. So to start out, I'm going to focus on this global scale, the global scale drivers of sea level change. And just as a quick overview and maybe a refresher for all of you. So there's really two reasons that sea level is rising on global scales. The first is the ocean is warming. When the ocean absorbs heat, the water expands and we have thermal expansion. So global oceans increase that way. And the other is that land ice melts and goes into the ocean. So from the ice sheets and glaciers, that ice obviously melts, goes into the ocean, and then sea level can then go up. And we can look at this in terms of what we call the sea level budget. So ice plus thermal expansion should equal the total sea level we change. Again, this is on global scales. Regionally, there's other drivers and you have differences of time scales, but very broadly on global scales, these are the factors contributing to global change. And we have observations over the past couple of decades of each of these individual factors, two coming from satellites, and then the other, the thermal expansion coming from in situ observations. And I want to talk a little bit about these observing platforms, how good they actually are in telling us what's causing these sea level changes to occur. So I'm going to start out with satellite altimetry, so this total sea level factor. So if we step back and think about how we've measured sea level change in the past, so over the last century plus, going back a couple of centuries, we've really just been relying on tide gauges to measure sea level change around the world's coastlines. And I have a couple images there. That's the tide gauge in the upper left image there. That's the tide gauge in San Francisco. On the right is a little schematic of how a tide gauge measures sea level. I'm not going to go into depth about that, but the point there, one of the points there is that tide gauges aren't necessarily located on land. So they're not just measuring the change in ocean, they're also changing the movement, or they're also measuring the change in the land relative to the ocean. So they're measuring relative sea level. And then that bottom panel there, I'm showing the distribution of tide gauges around the globe. A couple things to notice. One, those tide gauges are biased towards the northern hemisphere. So most of the gauges in the northern hemisphere, and you can see there's large swaths of the ocean that are just not covered by tide gauges. You need an island in the open ocean in order to situate a tide gauge. And that leaves a lot of the ocean just unmeasured by these tide gauges. So there's a lot of challenges trying to take this information, these observations, and understand what's happening in terms of global sea level. And I'm going to refer to something as global mean sea level. That's basically taking the observations we have around the world, averaging them at any given point in time, and then building up a time series. So over the past couple decades, there's been a significant advancement, and that comes from satellite altimeters. So the modern satellite altimeter record goes back to 1992. Satellite altimeters have been measuring the sea surface height of the ocean with near global coverage, and it's been continuous. So since 1992, we've always had a satellite altimeter on orbit measuring sea level. And the measurement principle here is actually relatively straightforward. So that satellite sends down a radar pulse from the satellite. That radar pulse hits off the surface of the ocean and then travels back to the satellite. And by measuring the time it takes for that pulse to get to the ocean and back to the satellite, and understanding very accurately where that satellite is on orbit, we can actually come up with a very good measurement of sea surface height, or the height of the ocean. And we can actually get this measurement to roughly the size of, to the accuracy of an inch. So from hundreds of kilometers up on orbit, we can measure the sea surface height accuracy to an inch, about the size of a quarter. It's a very impressive measurement. Obviously, there's a lot of other corrections and things that go into this, which I'm not going to get into. But the underlying measurement principle is relatively straightforward. So this past November, we actually launched the Sentinel-6 Michael Freilich satellite that's going to continue this record into the future. So that is collecting measurements on orbit now and providing us further measurements of sea surface height. And yes, I do know it looks a little bit like a house that's been noted, or Snoopy's doghouse is how it's been referred to. That's just the most efficient design for what was trying to be accomplished. Not intentional. I get that question a lot. But this is a little schematic of, or a little cartoon of how this satellite measures on orbit. So it actually is measuring directly below the satellite. So the satellite maps out a particular ground track over the ocean. So you're not seeing all of the ocean, but over the course of 10 days, you have what we call the repeat orbit. So every 10 days, the satellite covers the full extent of the global ocean. With other altimeters we have in orbit, we can fill in some of these gaps, and you end up getting a nice clean view of what's happening in the ocean at fairly high resolutions. So again, just to be clear, it is measuring directly below the satellite as it flies, and then you build up those measurements with other altimeters, and you can come up with a map like this. And I want to show one other video. Let me go to the next slide here, see if this works. One other video here. So this is every 10 days, or what we call a cycle, we can look at the observations from these altimeters. The resolution will improve in just a second, or should. So this is the Topex Poseidon altimeter that launched back in 1992. And you can see these ground tracks, but an important feature here is you can see all the propagating features, everything that's going on in the ocean. So it's certainly not a static ocean. We'll come back to that in a little bit here. But you start to build up these observations, and you can get a really good estimate of global mean sea level. Here you can see an El Nino developing in the Pacific. And then in 2001, we launched the Jason-1 satellite, and you can start to build up this record. So this goes all the way through. I'm not going to let this run all the way, but we can go all the way through to the present with these types of images. But this really gives you an idea when we compare back to what we saw with the tide gauges that are very limited in their sampling along the coast of the ocean. Here we get a very nice, complete global view of sea level change. So if we take all these observations and we average them together, you end up with this. So this is the global mean sea level time series as measured by satellite altimetry. There's a couple things to note here. One is that it's relatively linear, right? There actually is a slight acceleration that's been measured and pulled out from this, but there are certain dips, obviously, at different times. A lot of those are related to El Ninos that might have occurred. But in general, it's a relatively linear record. And we can measure that rate of rise very accurately. So about 3.4 millimeters per year, or 1.3 inches per decade. So from these altimeter records, we have this really good understanding of why global mean sea level is changing. Not necessarily the processes causing it to change from this alone, but we know why sea level is changing. We know how fast it is rising. So, and I mentioned that we just launched Sentinel-6 last year. So this continues the 27 plus years of sea level measurements. So this is kind of the track we have here. The Topex Poseidon was the first to be launched. And then we went into the Jason series, Jason-1, Jason-2. Jason-3 is actually still on orbit, and we've launched Jason-CS or Sentinel-6 just last year. So this is a really important scientific achievement to have this long continuous record. And I sometimes get the question, well, why is it so important to have this long record? And I'm sure a number of you can come up with answers for this. But one reason is that if we do these comparisons between the satellite data, so what I'm showing in red or orange there, on top of what we can infer from the tide gauges, which is in blue, you can provide context for what we see during the satellite record. So one thing to note is that sea level is rising faster now on global scales than it has at any point during the 20th century, looking at this tide gauge record. So it provides important context for this very high rate of rise that we're seeing over the past 3 decades. But we can also see that as we start to build up this record, there are other factors that might come into play. So you can see from this time series here that between, say, 1950 and roughly 1980, global mean sea level was relatively flat. We didn't see much of an increase. And this was actually associated with a rapid increase in the building of dams and water impoundment. This actually caused global mean sea level to flatten out and stay pretty stable over this time period. So again, as we start to build up these longer records, we can really understand the changes that are occurring now, how they relate to the past, and that'll help our understanding for how they may change in the future. All right, so I've covered total sea level. Now I'm going to shift to the ice side. So GRACE and GRACE follow-on, a different satellite observation system. So this is actually a really cool observation system and very interesting to understand how it's actually measuring changes in ice and water around the Earth. So it's the Gravity Recovery and Climate Experiment. So GRACE, the first one of these, launched in 2002. It stopped working in 2016, and then GRACE follow-on launched in 2018, and it's still making measurements on orbit. So there was a slight gap between these two satellite records. But all that GRACE is doing is measuring gravity changes in Earth. And actually the only measurement it's making is the distance between the 2 satellites that make up GRACE and GRACE follow-on. So I'm going to play this. I've got a number of videos here just to try to improve the understanding of how these these are working. I'll turn off the sound there. So again, these satellites are on orbit, and the only measurement they're making is the distance between them. And that distance changes depending on what's underneath the satellite as it orbits the Earth. So on the right here, you can see that that first satellite, as it approaches something that's very massive, has large gravitational pull, it gets pulled towards that. And the distance between the two satellites increases. Now, as that one flies over and the second one catches up, that distance decreases because they're pulled back towards each other. And there's this constant interplay, and you can kind of see in that video on the left, there's this constant interplay between those satellites as they fly over the Earth. And as mass changes, as water moves around the Earth, as ice melts and moves from on land into the ocean, GRACE picks that movement up and it can measure it very accurately. So it's not actually making any direct measurement of what's on the Earth, it's really just making that measurement between the two satellites. All right, and then from that, so here I'm showing the GRACE and GRACE follow-on observations over Greenland. Let's see, yeah. So this is starting out in 2002. So not only can we tell that Greenland, for instance, is losing ice, we know exactly where it's losing ice from. Okay, so we can identify particular parts of Greenland that are losing ice more rapidly than others. This is important scientifically as we start to understand how changes might happen in the future. And we build up this nice record, and we'll let this run all the way through. Let's see. And then I can do the same thing for Antarctic. And you can see that there's this little gap that's on here between GRACE and GRACE follow-on. But you get these really nice measurements of where mass is being lost. And it's actually interesting for Antarctic, the Antarctic, because you do see some areas during this time period where you see slight increases at different times in the ice accumulation. But then overall, certainly we're losing mass from Greenland or from Antarctic. Okay, so now if we take those measurements, so we take the GRACE measurements, we have this understanding of the movement of water between land and ocean, and then we can estimate the contribution of that movement to global mean sea level. So that's exactly what this is showing. So this is sea level change specifically. It's largely driven by ice loss. On shorter time scales, it can be related to the water cycle or interannual to decadal changes in the water cycle. But we know from 2002 to present that ice loss has contributed about 2.1 millimeters per year to the global mean. So if you remember back, we had about 3.4 millimeters per year from total sea level. Here, we're looking more on the order of 2.1 millimeters per year. So about 2/3 of the sea level rise we've seen over the past couple of decades comes from ice loss. All right, so the last piece of the puzzle here is the thermal expansion that we have from the Argo profiling floats. So this is not a satellite observation platform. These are in situ observations. And I'm just going to have one slide. I don't have a cool video. This isn't actually a NASA. It's a NASA instrument. Certainly we rely on them, but yeah, I don't have any cool videos to show for this one. But these floats are in the ocean, and every 10 days they drift under the surface. They descend, and then they measure salinity and temperature, a salinity and temperature profile from about 2,000 meter depth to the surface. They surface and then report that data back out, and then they continue this process until either they stop working or they run ashore. But I think there's roughly 4,000 of these in the ocean right now, just drifting around, profiling and providing us information about subsurface salinity and temperature. So from these measurements, we can then estimate the impact of thermal expansion on sea level rise. So we take all the observations we have around the globe, we sum them up, and then you end up with another time series. So this is the Stericite specifically from Argo, slightly different time period. So this record started in 2005. It's continuing up to the present. And we're at about 1.1 millimeters per year from the Stericite. And for those of you doing the math in your head and keeping track of it, as we go back to this equation, you can see that the numbers are going to work out, at least in terms of the trend. So we have the ice plus thermal expansion, and it should equal altimetry, and we can check this very easily, and that's what this is showing. I know there's a lot going on here, but the two things to pay attention to, the blue line, that's what we have from altimetry, and the yellow line is the combination of Argo and GRACE. So you can see that in general, these two line up pretty well. It's pretty good agreement. What this does is it allows us to have confidence that we understand why sea level is changing on a global scale, and then we can start to monitor those changes as we go forward. So this is nice independent confirmation of the different observations that we're making. The pieces fit together, it matches our scientific understanding. And I say that with a slight caveat because there is a known issue in this budget closer show. So I generated this really quickly yesterday. This is the latest data. I'm doing the same comparison where Grace and Argo is in red, and then I have this, the altimetry in blue. And you can see since roughly 2016 that we've started to see a little bit of an offset between the two of these. And it's been it's been the subject of a number of different scientific studies trying to understand exactly where this mismatch comes from. It's possibly related to the launch of Grace follow-on. More likely it has to do with the Argo profiling floats. But by doing this monitoring, we can start to, we very quickly can identify where there might be a problem in one of the observing platforms. So again, this budgeting kind of study, it's certainly important scientifically, but from an engineering perspective and trying to make these measurements, it's also very important. All right, so I'm going to shift gears from the global to the regional. And this is a little bit similar to the map I showed, or the video I showed with the along track data and some of the propagating features. But here we've gridded up all the available satellite altimetry just to show how things are moving in the ocean. So the first takeaway here is that certainly the ocean is not a bathtub. There's a lot of roughness in it. There's a lot of different signals, a lot of propagating features. In a second, you're going to see the big El Nino in the Pacific come up, the 97, 98 El Nino. You can see it right there. And these are large signals. So that El Nino, for instance, is on the order of 40 centimeters per year in the Eastern Pacific and off the west coast of the US. So these are big signals that really drive sea level change. So with these altimeters, we can not only understand how sea level is changing on global scales, we can also understand how it's changing on regional scales. So if I take this data, the underlying data here, and I compute a trend for every location, so understand the rate of rise at each location, you end up with this map. So at face value, and that scale down there is a little bit hard to see. So from about, let me see, it's roughly between 5 and -5 millimeters per year. I think this is kind of a weird scale here, but the point is that sea level is rising almost everywhere. You see a little bit of blue, which shows sea level fall, and some of that's just related to very high frequency variability that's kind of aliased in here. But in general, sea level has risen over the past 3 decades. And you do see, if we focus in on the US, for instance, you do see some regional variations. Off the west coast of the US, we've actually seen relatively little sea level rise over the past 3 decades, whereas on the Gulf Coast and East Coast, it's been a very rapid sea level change that's occurred over the same time period. So these altimeters provide us a really clear look at how sea level is changing regionally as well. And a couple notes. So as I said, I mean, the ocean is really not behaving like a bathtub. So when that ice melts, when there's changes in what we call the stereodynamic, or like the ocean dynamics plus the thermal expansion portion of this, it maps onto sea level and it affects sea level in a lot of different ways. So sea level is really changing on a very wide range of space and time scales. And you can see that from that previous video. There were a lot of propagating features, a lot of features that come in and out over time. And then certainly we had the long-term increase. So some of the contributions to this particular pattern, some of the things affecting this pattern. So natural variability signals like El Nino and the Northern Atlantic Oscillation on the East Coast, these can drive sea level trends and affect sea level trends over these relatively short time periods. So just as an example of this, I had already mentioned this 97, 98 El Nino, that's the one on the left here. So it is this very large signal. You can see that propagating up the west coast of the US with a relatively big sea level change. On the right there, this is a more recent 2015, 2016 El Nino. And again, you see something similar where you've had very rapid increase in sea level over a short period of time, year to year, that affects sea level on the west coast again. And you can also see there on the difference between what we see in the East Coast in 1997, 98, and the Gulf Coast, and what we see in 2015, 2016. There are these dramatic differences on the order of tens of centimeters that occur over these shorter time periods. The other thing to note is that when ice melts, it doesn't go into the ocean. It doesn't fill the ocean like a bathtub. So it actually affects the gravitational signature of the Earth, right? So when ice melts from Greenland, for instance, so what we call a fingerprint, a sea level fingerprint for the Greenland ice sheet is in the top, the bottom is the Antarctic ice sheet. So when you lose mass from Greenland, you've actually you've lessened the gravitational pull towards Greenland. So that water that was initially pulled towards that mass, towards that ice, is no longer pulled in the same way. So you actually see sea level fall directly around Greenland. And then as you get further afield, you see a more dramatic increase in sea level associated with the mass loss from a given source. So for instance, in the top panel, we're losing ice from Greenland. it's actually the southern hemisphere that responds most heavily to that mass loss. So that's where sea level increases the most. The opposite effect occurs in Antarctica. So when we lose mass there, then it's the northern hemisphere that's most affected. So in terms of the United States, one of our main concerns certainly is what happens in the Antarctic ice sheet, right? So if we lose mass there, we're going to be more heavily affected than the global mean. And just one note, that black line that's there is the global mean. So it's a value of 1 essentially. So for anything above or below that line will be less or more depending on where you sit. But from that, we can then go one step further. So for a particular location, we can understand exactly where melt from a particular source is contributing to sea level rise in that location. So on the left here, I have New York City. On the right, I have Sydney. And you can see that you should note the scale there is a little bit different from, so New York is 0 to 0.3 millimeters per year. Sydney is 0 to 0.6 millimeters per year. So you can see that for Sydney, Greenland, for instance, has a much bigger effect, almost double the contribution than what we see in New York. So GRACE and our understanding of sea level change, it really allows us to identify what sources of ice we should be monitoring, for instance, for a particular location. Where are we concerned about losing ice if we're on the East Coast of the US, as an example? And from GRACE, we can get that information. All right, and then the last point here before I jump into the sea level change team, we also measure coastal subsidence with satellites. So we use something called synthetic interferometric synthetic aperture radar, or INSAR. I know that's a bit of a mouthful, but essentially this satellite flies overhead. It makes a measurement at one time and compares to what happens at another time. So in that top right, you can see a really dramatized version of this. So that house, certainly, hopefully nobody's living in a house like that, but at one time you measure where that house sits. The next time, maybe it subsided somewhat, and then there's a difference in the phase and the amplitude of what that satellite is measuring. And from that, we can back out an estimate of vertical land motion or subsidence around the coast. And what's important here is that it happens at very high resolution. So you can get down to almost street level with these observations. So one example of this is for Norfolk, Virginia. So this is a recent NASA study using INSAR in the Hampton Roads region. And from this, we can go in and look at subsidence at very high resolutions. It's a little difficult to map. If you were to zoom in, you would get down to that street level, and it looks a little speckled just because the dots are on top of each other, just in terms of the plotting of it. But the point here is that we can get very high resolution estimates. We can understand how subsidence for Norfolk, for instance, varies across the region. It's basically understood that Norfolk and the mid-Atlantic are subsiding because of a couple different factors. Here we can assess not only whether it's subsiding, but also how much that rate varies in the different neighborhoods. So again, it's very valuable information as we start to transition this from the research world into the hands of planners who may be able to actually use it and the different planning or adaptation efforts they might take on. All right, so to connect this back to the NASA Sea Level Change Team, so NASA is certainly very invested in monitoring the processes changing sea level and providing that understanding of why sea level is changing now and how that compares to what's happened into the past. So from these observations, we know why, how, and how much sea level is rising over the past 3 decades. So those observations really provide a good foundation for this understanding. And we also know that a wide range of sea level processes can lead to coastal impacts. They can cause flooding to occur. As again, I'm showing the simple cartoon from the first slide. As these different factors stack up and how they interact in different timescales, it can really affect your potential for flooding at any given time. So these satellites are going to provide a critical role in monitoring these processes and hopefully providing information to coastal planners to take and to put into their adaptation plans. But I think it's important to note that these satellites don't measure all the relevant processes. This is a snapshot of the processes that are measured by NASA satellite, but certainly there's other ones that are not. And many of these are very high frequency. So tides, waves, storms, things like that, they're more difficult for us to assess given the sampling we have with satellites. And we also recognize that there's a need for integrated assessment. So it's not enough to tell you how, give you a projection of background mean sea level out to 2100. It's important to assess how that interacts with changes in tides, changes in interannual decadal variability to provide this complete assessment that's integrated across timescales and matches the particular need of a practitioner at the coast. So NASA is interested and hopeful that we can provide useful information. So in order to do that, to shift beyond the realm of science into something that is ultimately useful, NASA came up with the idea for creating the NASA Sea Level Change Team. So the NASA Sea Level Change Team was created in 2014. It's 70 plus scientists from across government agencies and academia. So it's a pretty diverse group. National, so it's focused on the US. And the web portal, so some of you may have seen it at sealevel.nasa.gov, that is directly tied to the Sea Level Change Team. So it was created in 2014 as part of the Sea Level Change Team. And now it's really the public face of the Sea Level Change Team. So any content you see on that website comes from the scientists in the Sea Level Change Team. The team leads, so Steve Neerum at the University of Colorado was the first team lead. I've been the team lead for the past 2 iterations. We actually just started our 3rd iteration of the team last year. And there's 2 goals of the team, and these have kind of shifted over time. The first is it's a NASA science team, so our interest is predominantly scientific, and our goal is to provide improved forecasts to sea level across a range of timescales. So take the understanding that I showed you previously, and then convert that into forecasts and understanding of future sea level change. And then the second that has come up over the past few years, we want to try to connect with practitioners and stakeholders and provide what I'm calling useful sea level information. And I'll talk about how we're trying to do that in the last couple slides here. But first of all, so I mentioned our primary focus areas on the science. We have a couple science objectives. I don't necessarily need to read through these because we've kind of covered these. But that third one, really to integrate these results into better forecast predictions and projections of sea level rise, understanding that we can take steps to convert our science into information that will hopefully eventually be useful for a practitioner or someone working at the coast. So the team is actually made up of 6 individual investigations, all with separate science goals. And then these 6 individual investigations come together to try to tackle interdisciplinary problems and address team-wide goals that including these forecasts that I'm talking about. So this team structure is actually really nice. It brings together different disciplines, different science disciplines, and allows us to work on some very complicated scientific problems. And just to be clear, we do cover kind of the full scope of the processes that change sea level. So I've listed those there. I mean, we have ice sheets, mountain glaciers, solid earth deformation, vertical land motion, ocean dynamics, terrestrial water storage. So we have hydrologists on the team. And then we also have some contributions from higher frequency variability. So there's some scientists working on that. So we really have the expertise to go in and tackle these difficult scientific problems. All right, so the second goal is this outreach goal. So it's really to provide useful information to partners, planners, and decision makers regarding ongoing and future regional sea level change. So we came up with this objective and we decided we need to take a smart approach to do that. So we're really focused on the following, and there's really one fundamental question to this that we're focused on. What is useful, right? So I have that word useful in the top line there, and it's something that's gotten thrown around a lot. On the NASA side, we talk about providing something that's useful, but it's clear we don't really know, or at least we didn't, and we're still working to understand what useful actually means. What is useful to a practitioner? And we are very wary of just doing things that satisfy our own curiosity as scientists. There are certainly things initially that we may think is useful or cool or a new tool or product that needs to be developed that can then be used by someone, but that it is, again, it's not a particularly informed view to have scientists telling themselves what they think is useful for someone else. So we're trying to go about this in a smart way and recognize where we sit on the information flow from the basic observation down to the stakeholder. And on that bottom there, I have a schematic that we're kind of working from on the Sea Level Change Team. So on the left, we have the observations. The NASA Sea Level Change Team takes those observations and then works with a boundary organization or operational agency, someone who actually has a lot of experience working with stakeholders, coastal engineers like some of you on this call right now, who can take that information and translate it to something that is ultimately useful. And the NASA Sea Level Change Team is trying to tackle certain parts of this. So certainly we recognize the first step is the observations. We have a lot of expertise in that. We then do modeling and analysis that's heavily funded as part of this team. We synthesize the model results, so modeling particular processes, we synthesize these into projections, for instance, or forecasts on different timescales, or potentially just a monitoring product. And then we try to take steps to convert that research into application by forming targeted partnerships with boundary organizations, other operational agencies. So we're trying to do this very common sense approach where we recognize what we have expertise in and then finding partners who have the expertise to ultimately make our science useful. So we also recognize there's a need to engage those translating science into action across a range of applications. So we've taken two steps. One, and perhaps the bigger one, is we formed a practitioner advisory board, and we've come up with objectives for that board. But really the idea is to have a set of practitioners who are well-versed in the science and who have an understanding of the needs of the ultimate end user, and to have them work with us as we say that we would like to develop a tool, to have them come in at the ground level and say, yes, this tool could be useful, or maybe you can make these adjustments and it would be more useful. They can also help us identify gaps. So if there's particular gaps in either the guidance that's put out or a particular observational gap that's there, they can help provide that back to the C-level change team so we can try to fill those gaps, or at least work in a way that that is recognizing that there are limitations and doing what we can to support C-level decision making. The other thing we're doing is holding annual meetings in locations that are impacted by sea level rise. So we have our annual C-level team meetings. We're trying to move these around and engage local stakeholder communities. One is to somewhat advertise the work we're doing on the team, but I think more importantly is to try to get an understanding by direct conversation and interaction with those stakeholder communities of what they need and what we could do to ultimately provide something that's useful. So our past meetings have been in San Diego, Norfolk, Annapolis. Our next meeting, it was actually supposed to be last year. Obviously, there was some challenges there. Our next meeting is going to be in Savannah, Georgia in the March-April timeframe, assuming that things continue on their current trajectory and an in-person meeting is feasible. So we're trying to take these two steps. Again, this is somewhat unique for a NASA science team, right? So it's not very common to interact and engage with practitioners like that, but we understand that we have an opportunity to take our science and the research investment that's being made by NASA and then transition that into something that is ultimately useful. And then one example of a tool that we've developed, and these are my last slides here, then I'll open it up for questions and stop talking. This is an evaluation and assessment tool that we produced, again, with feedback from the stakeholders and the practitioners that we're working with. So we're taking the different observations and doing the kind of budgeting study that I showed previously, but at specific locations, tide gauge locations around the US. It also provides easy access to satellite and in situ data, so satellite altimetry and tide gauge data you can pull down very quickly for a given location. And we're trying to support this with easy to digest and very accessible explanations of the science that underpins the different measurements we're making. So just to go in here, so this is just for San Francisco, for instance, and we can separate out the different drivers. We can see how well we understand the processes contributing to the sea level change measured at the San Francisco tide gauge, for instance. Provide that in a nice, clear way. I'm not showing the full depth of the explanations and kind of the content supporting this, but this is just a quick snapshot here. We have these comparisons between the altimetry and tide gauge. You can toggle subsidence on and off, see how subsidence is contributing to the tide gauge record. And then you can very quickly download the data that underlies all of this. And the last piece here, we also have simple access to the GPS that's available in the region. So how we actually measure vertical land motion. I talked about NSAR, but GPS obviously provides very good measurements of vertical land motion around these different coastal locations. So again, you can download this data, the GPS, the tide gauge data very quickly and easily. And we're tying this back to other content that's on the web portal on sealevel.nasa.gov. So again, this is one example of how we're trying to use that input from practitioners on the front end and trying to understand how we can actually create a tool that's useful. And we'll have this ongoing engagement and feedback cycle where we can start to add capability or adjust to these tools that we're producing. The goal here is not to just keep throwing out more products and tools, it's to try to clean up some of the information that's out there and provide a tool that is ultimately useful and maybe unique to what is already available on other platforms. All right, so yeah, I'm not gonna, just in the interest of time, I won't read through all these different summary items here, but I think the key thing here is that NASA has these satellite observations. They give us this foundational information for understanding why relative sea level is changing on both regional and global scales. And then the sea level change team is really interested in taking that understanding and try to go the next step. So in a common sense approach, go the next step, work with practitioners and boundary organizations to take our science, which has really advanced very rapidly in the past couple decades as a result of these observations, and provide something that is useful. And then just a last point, next up for the sea level change team, there is a vertical land motion product or delivery tool that we're coming up with that will provide GPS and InStar observations where they're available around the globe. The team is very actively working on improving regional relative sea level projections, focusing on a range of timescales. So that's a process that's playing out. And there's also some work being done on seasonal to decadal sea level predictions. So these are some of the active team-wide activities going on with the sea level change team right now, and should be coming down the pipeline in the near future. And with that, I will finish up and take any questions. Thanks.
All right, great. Thanks for that presentation, Ben. A lot of really neat information in there. So just as a brief recap, I guess, for the questions, you can either use the chat down at the bottom. I see we already have a question down there that I'll get to, or you can also use the raise hand feature, and then Sean will be able to unmute you and you can actually verbally ask the question as opposed to having to type it into the chat. So those are the two options that we have. And the first one that we have here says, Dear Dr. Hamilton, can you briefly explain why and how tides can change in time and how you can measure this effect in order to remove the contribution of changing tides from the measured sea level? For example, measured with local tide gauges. Can modern tide models like FES take into account these changes? And are these models appropriate to remove the tide contribution from in situ sea level measurements? Thanks a lot. Very nice webinar.
Yeah, so there are a number of important questions in that. And we actually have one of the experts on this call, Thomas, one of our hosts. This is definitely more up his alley than mine. I will say one comment, maybe I'll kick this to Thomas to address, but the altimeter measurements are very carefully corrected for tides. So with that repeat orbit that I talked about, you have the potential to alias tides into your information and really confuse the signals that you're seeing. So there's a very active part of the satellite altimetry science teams and engineering teams that are correcting for those tides. In terms of changes, Thomas, I don't know if you want to jump in. You had a very recent paper that discusses this.
Yep, I mean, as Ben mentioned, altimetry data is carefully corrected for the influence of tides, but changing tides, of course, are a problem, especially as we have shown in a recent study in urbanized estuaries, where we have affected and altered the depth of channels quite a bit through dredging that has been going on for decades, sometimes 100 years, 150 years. And that has led to pretty significant changes in tides. And that is something we can, of course, correct for when we do a tidal analysis, and instead of analyzing the full data set, we do it on chunks of the data, like year by year or 5-year periods. Then we can really identify these changes in tide. But of course, those are very hard to predict into the future. We know that sea level rise itself, if it's large enough, at some point will have a pretty significant impact on changes in tidal amplitudes. But the vast majority of the changes that we've seen in the past are man-made. And that depends very much on us, on how these develop into the future. If we stop dredging or even infill some of these dredged channels to go back to a more natural state where we were 150 years ago, we would see a response, of course, in the tide level as well. Does that clarify the question?
I think it does.
I think it does. Yeah. Thank you, Thomas. All right. So we had a question from Doug Mann. Can you comment on the role of the Gulf Stream to affect sea level on the U.S. East Coast? And can you comment on the reported slowing of the Gulf Stream?
So yes, I mean, I think that based on the question there, I mean, you kind of know the answer here. So a slowing of the Gulf Stream does cause sea level to increase on the East Coast, directly along the coast. And there have been some recent studies talking about slowing of the Gulf Stream, not only in more recent observations, but also some evidence of that using tide gauge records and some sophisticated statistical models that have been set up. So it is something worth monitoring. There is a challenge with studies a slowing of the Gulf Stream and really of any kind of trend that we see during the satellite record is that interannual to decadal variability certainly does influence the trends that we're seeing. So trying to get a good separation of what might be causing, say, a slowdown in the Gulf Stream on shorter timescales from a long-term, maybe climate change driven signal, that's a real challenge, and it's active and ongoing research. So I know that's not a very concrete answer to your question, but at least it is a comment on it, I guess.
Thanks for that. All right, then the next question says, is the coastal subsidence data available globally or only across the US?
Yes, so on the US, we are in a pretty good situation, and I didn't show a map, but we have very good GPS coverage along the coast of the US. The situation is not the same everywhere across the globe, and in some areas, GPS coverage is very limited, or it's just not there. The NSAR work has the potential, it can potentially be done anywhere, but it's relatively expensive to do this kind of processing to get to the NSAR observations everywhere. So it's really, if someone is paying for it, then it has been done for particular locations. So to better answer your question, there is very good coastal subsidence data on the US from GPS now. There are dedicated NSAR studies for the US now, and there's going to be a rapid expansion in availability of NSAR for the US specifically. It's much more diverse in terms of the coverage globally. But there is some, I should say, there is certainly coastal subsidence data available globally. It just depends on where you're looking, what location you're looking at.
All right, thanks for that.
Chris, we also have a raised hand from Samuel DeBartolo. If you want to go ahead and unmute Samuel, you can ask your question.
Sounds good. You see him still as muted. Are you able to unmute him, Sean, or maybe it's on the other? There we go. Can you ask your question, Samuel? We still can't hear you if you are asking it.
Sounds like we've got you now, Samuel.
Sorry?
There we go. I can hear you now, Samuel. Can you ask your question?
Okay.
All right. Unfortunately,
Can you see?
Unfortunately, it's coming in really spotty, at least on my end. I don't know if Ben, if you heard a question there or not. Samuel, can you just type your question in the chat? We'll make sure that we get to it.
My question is how it is possible to participate at the NASA team, and if there some smooth scaling or multi-scaling approach in the local scale and the global scale in the analysis of the sea level. So this is my question, because
Yes.
what if there are scaling approaches about these?
Yes, so what I've covered here is very observationally focused. So our interest is certainly, I showed a lot on global scale and regional scales. Our interest is in really getting local projections and getting as local as possible. And I think that's kind of the point I was making, where we need to bring in or have good partners or rely on other members of the science team to bring in some of the more local information associated with tides and some of the other changes that are relevant. So I don't have a great answer to your question other than to say that we are trying to work and see how the processes that happen on global scales combine with what happened on local scales.
And then the first question, Ben, related sorry, go ahead, Samuel.
Sorry, can I just another questions? fluctuation can be or this scaling depends of the simple or multi-scaling about these measures.
Yeah, I only
Unfortunately,
got very limited part of that question.
yeah,
Tim.
Samuel, that question, only about half of it came through on the audio. If you type it in, that may be a little bit easier. There seems to be a little issue with the audio. The first part of his question, though, Ben, and other folks might have it as well, was he asked how an individual could possibly participate on the NASA team. At least that's what I heard. So I don't know if there's any way you can address that.
Yes, so it's a competitive call put out by NASA. So you have to submit, and then it's reviewed by a panel, submit a proposal and reviewed by a panel and selected for funding. So that's the main way to be a member of the sea level change team, but you can certainly engage with members of the sea level change team and work with us. And if you have particular needs or information needs or a question, you can certainly contact me, or, I mean, if you go to the portal, sealevel.nasa.gov, there's a tab where you can click on the project team and get contact information for everyone. We're always open to those kinds of requests and partnerships.
All right, thanks for that.
Thank you. Thank you. Thank you.
All right, the next typed in question comes from the Coastal Engineering Sciences Committee member, Bill Daly, who says, in slide 11, there appears to be a section of the tide gauge record between roughly 1920 and 1960 that indicates a rate of sea level rise that rivals or is potentially greater than the most recent satellite data. You care to comment or offer an explanation? Wonderful talk, thank you.
Yep, so it's a good catch. So the one thing you'll notice is not shown here is the uncertainty. So the uncertainty is much larger as you go further back in time. And that time period of increase, it does come close to what we see with the altimetry, but it's less sustained over 3 decades. But to address your question, the mountain glaciers and the Greenland ice sheet were really picking up steam during that time period in terms of the mass loss. So they were contributing very heavily to sea level rise. And without a particular factor such as dam building or water impoundment, we saw a rate that was actually very high. Again, with a caveat that it's pretty uncertain during that time period. So there's a big difference in the uncertainty for the last 3 decades versus those first 3 or so.
All right, thanks for that. The next question comes from Hugh, who said, when the GRACE satellites are orbiting, their relative spacing changes. Do they change their elevation from changes in gravity as well?
Yeah, with both the altimetry and the GRACE satellites, it's very important that we know where the satellites are. So any changes in orbit or in elevation, things like that need to be corrected for or accounted for. So there can be deviations, small deviations, and there's ongoing monitoring of that as part of all these satellite teams.
Okay, great. All right, Stephen asked, how do the predictions of 2021 sea level made back in, say, 2020 compared to the observed sea level in 2021? Has the sea level rise been more or less than what was predicted? Does the data for future predictions take into account these inaccuracies? Yeah,
and I think I saw you clarified that he was comparing 2021 to 2000. So this is very active research, something that I've been looking at very recently in terms of how the predictions we've had or projections we had previously match up with what we've actually seen over the past couple of decades. A big challenge here is that it's a relatively short time period, and the coasts of the United States, for instance, have been heavily impacted by interannual to decadal variability, so natural variability. So it's really coloring our ability to separate out what is actually going on. That being said, that for the Gulf Coast, Southeast, and Northeast coast, we've seen very high rates of sea level rise and accelerations of sea level rise during the altimeter record that have outpaced most of the model projections. For the West Coast, it's been heavily influenced by decadal variability. So we've actually seen a little bit less than projected, but with a high acceleration that's taking place. And that's a part of that's coming out of some of the decadal variability that we've seen. So yeah, I think there's not a more or less answer necessarily. It varies by coastline. And you have to be very careful to consider the other drivers that are affecting sea level. But I would say that based on what we've seen from the altimeter record and the recent tide gauges, we're towards the upper end of the model projections, like from the Sweet et al., the NOAA report that came out in 2017, that comparison.
Got it. All right, great. Mustafa from the committee asked, in your future sea level rise projections, will it consider climate change physics or be fully statistical based on data?
Yes, so we have both modeling efforts and probabilistic models that are funded as part of the team. So the quick answer to that is a combination of both. So the team is involved in assessing what we get from models versus what we might get from more of a statistical or probabilistic approach, or I should say fully deterministic versus a probabilistic approach. So that assessment's being made within the team, and it will definitely be reflected in any projections that we put out, that assessment.
All right. And then the next question is actually one that I had as well. Does your team collaborate with the Intergovernmental Panel on Climate Change, or IPCC? And if not, are you planning to do so? And the second question is, how do you plan to affect the scientific advice on sea level rise to a wider audience at the global scale?
Yep, so there's several members of the sea level change team that are involved or authors on the IPCC. So there's that direct involvement. One of our goals too is to, when the IPCC, the AR6 comes out, is that we reflect that information and that in terms of the sea level that's in that report on the portal. So we're actually going to host the projections from AR6 on the portal, have a nice visualization tool, and provide the context that we have from the altimeters and from GRACE and all these other pieces. So we'll give it a framing of the sea level change team, but our goal is to communicate what's in the IPCC and potentially a user-friendly way, working with those practitioners to work on our guidance that we put out. So I think collaboration might be the wrong word, because we have members on the IPCC and we're planning to take the output of the IPCC, and a lot of our science went into it. So there is a very close connection between the sea level change team and the IPCC. The second piece, a lot of our stakeholders, just in terms of the geographical scope of the team, are national, are focused in the US, but the observations we have are really global in scale. So if you go to sealevel.nasa.gov, you'll see that almost none of it is just focused on the US. It's all global in scope. Our issue now is just having the capacity to engage with stakeholders and practitioners on a global scale, but it is something we hope to expand into. Right before this, for instance, I was on a call with the WCRP, which is a global audience, talking about some of the ways the sea level change team can contribute to those efforts. So we are doing whatever we can to make those connections.
Great. So a follow on there, I guess, is I know, just within the US that, say, the US Army Corps of Engineers has their sea level change guidance, and NOAA has their products, and FEMA does things a little bit differently. So, I think some national strategies might be a little bit more cohesive than the US. Do you feel like there's a movement towards coming together across different federal agencies and platforms, or do you think it will stay kind of diverse with different agencies having their own guidance and numbers?
That's a really good question. So my interest is on getting better coordination and better alignment between these different agencies, and there are some venues where that's taking place. There's a kind of reinvigorated USGCRP effort to bring in the different agencies and to try to line up the guidance we're putting out, as opposed to, say, the sea level change team just created a new portal and just repeating what's already been done at NOAA or the Army Corps, for instance. So my interest and the interest of the NASA sea level change team is to align as closely as possible. One big step that's in that direction, so the NOAA report that had projections for the US that came out in 2017, we're currently working, and I say we because I've been brought into the author team, working on an update to that right now. So a new interagency technical report that'll come out later this year that involves scientists from NOAA, Army Corps, EPA, now NASA, trying to better take advantage of the different information, observations, and expertise we have across the federal government. So it's a very difficult problem. Everyone has to give up a little bit in order to contribute to better coordination and alignment, but there seems to be a willingness to do that. So we'll see where it goes.
Yeah, I think that's would be a great initiative to try to combine some of those things. It'd make it easier for someone to know what value to use and looking at different sources and finding kind of different information. So
yeah, exactly.
A recent question just came in from John Jones. I realize that we're a little bit after 1. We can continue on for a little bit here. for those that want to stay on. The question is, are changes to the mass distribution on the Earth that have a measured impact on Earth's rotation also having a measurable impact on sea level? He said, and then in parentheses, or in parentheses, earthquakes.
This is definitely outside my area of expertise. I believe the answer is yes. I don't have particular research, or I can't quantify that in any way, any measurable way. So I'll just leave it at that for danger of saying something incorrect.
Okay. All right. So any other questions that we have out there typed in or that people want to chat? While we're waiting to see if there's any other questions, I will mention that our group has lined up our next webinar speakers. So in the June, July type timeframe, we plan to have Dr. Brian Bledsoe and Dr. Todd Bridges. Dr. Bledsoe is from the University of Georgia Institute for Resilient Infrastructure Systems, and Dr. Bridges is with the U.S. Army Corps of Engineers and works with the Engineering with Nature initiative. So they plan to do a joint discussion on kind of sustainable engineering along the coast that combines the resilient infrastructure as well as engineering with nature aspects of things. So keep your eyes open. That will get posted on the COPRI LinkedIn page as well as some other platforms, but we do have those two individuals lined up for our next webinar. Let's see, any other questions come in? All right, I know we had several students out there. Any student questions from COPRI student chapter members or anything like that? Even if it's not specific to this talk, we want to make sure we engage with our students that are out there. All right, well, I think it wouldn't be too hard to find Ben's contact information if you do have any follow-up questions, or send them to me and I could get with Ben and respond. This was recorded, so if you know individuals that were hoping to attend the webinar but weren't able to, COPRI will process the recording and then post it to its YouTube channel. Our first webinar that we had with Dr. Chris Massey of the Corps of Engineers speaking about the South Atlantic Coastal Study is up on the YouTube channel now for anybody that wants to watch that one. This one will be up in the next couple weeks. And I thank everybody for joining in. Sean, do you have any closing comments before we close down?
Yeah, I just want to thank Dr. Hamilton for coming and giving this really great presentation. And Chris, you and the Coastal Engineering Sciences Committee for putting on this great series. We're really looking forward to the next one. Everyone who registered and showed up, we really appreciate it. Like Chris said, the video will be on COPRI's YouTube channel, along with the first webinar and a couple other great ones for you to look out for. You can always see all of COPRI's events on our new events calendar, which I've just dropped the URL into the chat. And also, don't forget to check out COPRI's committees and membership opportunities. And if you ever have any questions about COPRI, you can email me directly at my email, which is also in the chat. And I appreciate it, and we look forward to the next time.
Thanks, Sean. All right, thanks again, Ben. I appreciate it. That was a great talk. Thanks for taking the time to make the presentation, answer the questions, and share the information. Pretty neat stuff NASA's doing. Thanks.
Thanks a lot. Appreciate it.
All right. Bye, everybody.
Thank you.